I was gonna say leave the lights off.
Oh yeah. Well, mom, I can have mom.
No, nah.
Because I like mom too. But
He needs.
not everyone. Just,
He needs to see us. I would imagine.
I would imagine.
How things been?
Pretty good. Pretty good.
Excellent.
Glad I didn't fail on analysis. Thank God. Whew. There's a bullet there. Have you started that homework, the analysis?
I got yeah, did a couple things with it. Right now I'm focused on wrapping up.
Linear vector spaces.
Aye.
Okay.
You getting caught on something though?
Huh?
You getting caught on something though?
No, I haven't looked at it.
So, good morning. You can hear me? Very good. Could you please pass it to him? Oops. So the homework results are really good. I will send you the PDFs this afternoon. This applies also to you. Hello. I will show you the complete solutions in a minute. I'm not perfect, okay? So the reason why I show you the complete solutions is that you can compare your results with that, what is correct. If you feel you deserve more points, please talk to me, okay? When it comes to the test, it is more or less about modifications of homework problems. So you will see 3 problems. One is first order. Think about my options. Think about the difference between linear and nonlinear equations. So you know how much time it needs to solve a nonlinear equation. So at this point, you know about my options. Okay. Then you will see 2 wave equations. One definitely involving expansions. And everybody should be absolutely familiar with the way to work with these expansions. And then there will be one problem without expansions. And again, think about my options. There are not many. You can use your notes. You can use the textbook. You cannot use your iPhone, any software to solve PDEs. No internet, okay? Otherwise, you can use whatever you want, even your calculator. What I will show you now is how to solve the homework problems. In some cases, I was very impressed by your creativity to solve the problems. Otherwise, I have to say, it took sometimes a couple of pages to come to the result. And on Monday, there are 3 problems, and you have 50 minutes. It is also about doing this in an efficient way. So when I show you the solutions, ask yourself whether you can speed up your calculations by doing it slightly different in some cases. So some of you came to the correct result, but with a significant effort. Yeah? So on Monday, it is not about doing long calculations. It is about knowing what to do and doing it quickly, and hopefully without any mistake. Yeah?
So this wave equation with the expansion, what do you mean by expansion?
Like in homework, yeah, I will show it in a minute. Yeah? Similar. A slightly modified setup. Yeah? Not any big variation. When you really understand how to do this, you are fully prepared for the test. Yeah? But that really needs a thorough understanding. Yeah? And it is clear that you can solve PDEs in different ways. It is also about knowing how to do it as quickly as possible. Yeah? So I will show you the solutions. I think in one case, I saw an incorrect problem. That is not good, because in this case, it made the problem significantly simpler. So please look at the problem. Yeah. Also, in a couple of cases, I saw kind of typos, little things, but this does not make it easier. So if there is a domain from 0 to L, it is not from negative L to L. It is from 0 to L. If there's a domain from 0 to 1, it is not from 0 to L. It is from 0 to 1. Yeah? So please look at the concrete setup of the problem to not lose 1/2 point after the other. At the end, it adds. So you have the problem here, and we follow our usual setup.
Professor? On problem 2, for the test, is it fine to just leave it without solving the differential equation?
Yes, except I will give you the formal solution structure that you have to apply. There are 2 options, okay? One option is this here, yeah? And the other option is that you see an ODE, and I will give you the formal solution to the ODE structure. And then you have to use it. Okay?
Thank you.
So one major thing is to correctly decide about the eigenvalues. This is not any little thing, that is a major ingredient of the solution. And I saw in 50% of the cases that you go with n going from 1 to infinity or from 0 to infinity. Both is possible. You will get full credit if there's no mistake. But the structure of the eigenvalues should be clear. Otherwise, I did not observe any real problem with respect to the first problem, except some typos, like there was no lambda n c in the Bn formula. When you do not have specified values for f and g, it is obviously just the way to leave an and bn as is. Everybody should have a complete understanding of the solution to number 2. So this will prepare you nicely for the test, okay? The problem structure follows the structure of problem 1, except we have a force. So you should be aware of these expansions for un and for u and f. And actually, you can work with such expansions for all the other ingredients in this formula, right? For u prime, u double prime, whatever. You can expand each function according to these eigenfunctions. Then it is just the cheapest way, the quickest way to come to the ODE. And this is a kind of non-trivial ODE. Some of you tried to solve it. That was very brave. Thank you for doing this. Otherwise, when we talk about the formal solution, it is just good to let it as is. If you see solution structure to this sort of ODE, and you are asked to use it, then please use it. Okay? So that would be not the way to say, thank you, I'm not interested. Obviously, it needs to specify, also when we talk about formal solution, it needs to specify all the ingredients of the solution algorithm, meaning the eigenvalues, as I said, and the initial conditions for the PDE, so for the ODE in this case. So then, I saw, so if there were questions about the homework, it was about problem 2. Yeah? So please be aware of the philosophy of doing this. And when you decide about the eigenvalues, double check. To see whether that is correct. With respect to problem 3, I actually did not see lots of problems, except typos, like integration from 0 to L, integration from negative L to L, no lambda n c in the Bn formula, and finally, if you will see an integral like this. Actually, you can have the tables of your calculus book with you. This is not the point of this class to do lots of work in 15 minutes, including solving non-trivial integrals. So just come with your tables, but when you see a concrete integral, you should provide a concrete solution. Okay? Yeah.
Small question. In question number 3, last line n, that's the power to minus 1, n plus 1 or n?
You can write it in several ways. You can write it as negative 1 to the n.
Considering the fact that our n starts in our
I got a question.
Yeah.
On number 3, should the second boundary condition for V, the one with the partial with respect to t, should that be the original x minus, or x times 1 minus x, and then minus the...
Yeah, thank you. That's correct. I wrote it a little too quickly. Yeah, otherwise there would be no input. So homogeneous boundary conditions and a 0 initial velocity and a 0 position and this term for the velocity. No, I think it's correct. Yeah, it's correct. I think all of you came to the correct conclusion about the big U, which is only possible by applying these conditions. So again, do you have a good picture of the test structure? Yeah? The first order equation, 2 wave equations, 1 problem involving expansions, slightly more complex, and 1 simpler problem that you can definitely solve without expansions.
regarding that complex problem you were talking about. So in question
Which
number
problem? The complex.
like a complex problem. So in question number 2, we have ut like as a single derivative. If we change that to a ux, how would that affect our solution? Can we still use the same procedure to solve that problem? Like in the question for the wave equation, we had like ut plus kut equals c squared uxx plus f.
Yeah.
And if instead of like ukut, we had kux, partial derivative in terms of x and t, is that going to change like the way that we solve the equation?
No, it does not solve the way. It just modifies the ODE. Yeah. So you get another factor in front of the un prime. So it just depends. So I will not challenge you with let's say things which we did not consider in class. So it follows the approach to the homework. It is simply about demonstrating a good understanding of how to work with these procedures. Yeah? Everything is clear? Yeah?
And roughly the homework question change out the boundary or anything?
Yes. And let's say minor modifications of asking the question, like so it all this will be absolutely in this framework. So we it will be not about doing things which you did not consider so far. It is about modifying, let's say, the initial and boundary conditions and slightly the question, but definitely in this framework. There's no trick, okay? It is all about understanding of how to do this. Yeah? And again, you can work with these expansions for all ingredients in this equation. So for UX, for UT, for U double T, yeah. So for each ingredient in these equations, you can work with such expansions. And then it is just about putting these expansions together, coming to the corresponding ODEs, and following the instructions. Yeah? Excellent. It was, for you, it's also good, yeah? So, So what we did so far was to look at the 1D wave equation, and we basically talked about bounded problems. And then we continued and considered the case that we have a function of more than of more than one space variable. So we considered a domain in the XY plane, and here we consider now another problem. So we expand in this way our knowledge of methods to solve these equations by considering a three-dimensional problem and an initial value problem. So we talk here about the wave equation in 3D combined with initial conditions for the infinite space. And an appropriate setup for this problem is to consider the Laplacian in spherical coordinates, which is given here in by the first formula. And the u here obviously depends on the radius r. And it also depends on two angles. It makes it kind of pretty challenging. And what we will do first is to focus on the case of radially symmetric solutions. So there's no change under rotations. And in this case, we can write the Laplace operator like given here. And for the following, it is simply convenient to look at this implied property of the Laplace operator. So r times du, the Laplace of u, equals the double derivative of r times u by r. So far, so good? Excellent. Then we will ask for what this is good for. So we have here a wave equation in 3D. What we would like to get, of course, is the solution to this equation under the constraint that we focus here on radially symmetric solutions. So this fact allows to replace Laplacian by the last term. So Ru differentiated twice by R. So given this structure, it is not very hard to find the solution, which is given by Ru equals F at R plus Ct and G at R minus Ct. The next three lines show you that this claim is correct. So this solution works. And what we get out of this is the general solution structure, which can be interpreted here as one contribution that represents an incoming spherical wave and another contribution that represents an outgoing spherical wave. So we will consider modifications of this setup in our next classes, but before doing so, it is good to have a thorough understanding of delta functions, because we will talk a lot about delta functions. And to make absolutely clear that everybody is on the same page, I will show you a few basic properties of delta functions. let me first explain. Okay? So what do we do here? We introduce here a theta function depending on a parameter n. And we introduce its derivative. Then we ask what is the effect of n, and that should be obviously here the same big N. So I try to illustrate in this way the variation of theta n and delta n depending on n. And when I went to school, my hand drawings were always criticized, so I hope you get the idea here, yeah? So for n is equal to 1, we have a smooth distribution, a smooth change between 0 and 1. As n goes up, so this is the dashed line applies to n equals 5, we get a sharper distribution, and as you can imagine, when n goes to infinity, we get the step function defined in this way. But still, we talk about a limit, okay? So it is still a smooth function defined by the limit. So in other words, the theta function, the step function or heaviside function, is defined via the limit n goes to infinity of the theta of n. And when we look at the derivative, we see here features like this. So obviously, we have here smooth changes and little variations of the derivative. As n goes up, we see an emergent peak here. And as n is 20, we see here a pretty good and sharp peak. And as you can imagine, and for the case that n goes to infinity, we get a distribution such that the peak height will go to infinity, and the width of this peak will go to 0. But still, we talk here about a limit, okay? And when we ask then what is the definition of a delta function, we can follow these settings here, and the simple conclusion is that we can represent the delta function as derivative of the step function. Yeah? Again, this applies to limits. What is your question?
So for all n, the value of theta at x equals 0, 0.5.
You can actually, you can write this in several ways. The exact meaning is that we define it as a limit. And this is usual notation that is applied for that. And one can handle it obviously in 3 different ways. One can say that it is 0 for x smaller and equal to 0, or this case. And then one can also say that at x is equal to 0, the theta function is equal to 0.5. All that are valid writings that are used in the textbook, and I followed here the writing here in this textbook. Again, at the end, it is all about limits. That is the exact definition. Let's stop here. Have a good time. See you on Friday.
These 3D cases are not going to be in the exam, right?
No.
Okay.
Relax.